Imagine trying to build an entire operating system.
Right, which is already a massive headache on its own.
Oh, totally. But then add a live interactive coding environment to that and an optimizing compiler
All at the same time.
all at the same time.
Right.
And now imagine cramming every single piece of that into one solitary text file.
It sounds impossible, honestly.
It really does. But today, we're unpacking a piece of software that does exactly that. Welcome to today's deep dive, everyone. We're glad you're here.
Yeah, thanks for joining us.
Our mission today is to explore this fascinating document we have. It's called deepdiveanalysis.-md, and it details this hyper-optimized, incredibly unique piece of embedded software called Mecrisp Stellaris, specifically version 2.6.5.
Which is just a legendary piece of code in the embedded space.
Exactly. It's a masterclass in extreme minimalism. But it's also a story about how the open source community is basically dragging this abandoned masterpiece, kicking and screaming into the year 2026.
Yeah, dragging is definitely the right word for it. It's this incredible collision of old school bare metal craftsmanship and modern developer tooling.
So, okay, let's unpack this because I want to make sure we don't lose anyone, right out of the gate.
Good call. To really understand why the community is pouring so much effort into salvaging this, we have to establish what it actually is.
Right.
Under the hood, Mecrisp Stellaris is a native code, self-hosted Forth compiler. And it's designed specifically for ARM Cortex-M microcontrollers.
But the thing that makes it such an anomaly in modern software is that it's written entirely in ARM thumb and thumb 2 assembly language.
Just raw, unadulterated assembly.
Which is wild.
Yeah.
For you listening, we're talking about one single .das assembly file per chip architecture.
One file.
That one file acts as the interpreter, the compiler, the optimizer, the dictionary, and the REPL, re-eval print loop.
Which is just the interactive prompt where you type commands and the kip executes them instantly.
Exactly. And when we say Forth, we're talking about a stack-based programming language, right?
Right. For those who might only be used to, Python or C, Forth operates on a completely different paradigm.
It's basically a whole other world.
Totally.
Yeah.
Instead of defining variables and passing them into functions, you push data onto a stack. It's a last in, first out data structure.
So if I want to add two numbers, I'm not writing add parenthesis 3, 4.
No, not at all. You push the 3 onto the stack, then you push the 4 onto the stack, and then you literally just call the plus command.
And that command just pops the top two numbers off, adds them, and pushes the result back onto the stack.
Exactly. It is incredibly lean.
And because it's that lean, it demands just absolute architectural discipline from the creator, right?
Oh, yeah. Matthias Koch, the creator of Mecrisp Stellaris, he built this hardwired register map to handle that stack. And that is the key to his blistering performance.
Let's get into that, because the document goes deep into the architecture. Normally, software keeps the stack in RAM, right?
Yeah, the main memory of the chip. But going back and forth to RAM costs clock cycles. It's, relatively slow.
Right. But Mecrisp bypasses that entirely. It keeps the top of stack the POS, which is the most frequently accessed piece of data permanently kept in register R6.
That is the secret sauce right there. Registers are the absolute fastest storage locations on a microchip. They're built directly into the processor core itself.
So instead of going to a filing cabinet, like the RAM or the parameter stack, every single time you need your most important file hand.
Yeah.
It's basically just glued to your hand, right? Their hand is the R6 register.
That's a perfect analogy. It never leaves your hand.
But I do have to push back a little here. I get that the glued to the hand approach is theoretically faster, but chips today run at hundreds of megahertz. How much speed does this actually buy you in practice?
Well, it buys you a lot when you're compiling on the chip itself. Keep in mind, this isn't running on a powerful desktop.
Right, it's a tiny microcontroller.
Exactly. And having the top of stack permanently in R6 allows for this technique detailed in the source called opcoding.
Opcoding, which is a form of Peephole optimization, right?
Yes. Think about that addition example. If you want to add the number 1 to whatever's on top of the stack, you just write 1 plus.
Sure.
A standard, naive compiler would generate a bulky subroutine call. It would save the state, jump to an addition function somewhere in memory, do the math, and then jump back.
Which wastes a ton of clock cycles.
Right. But Mecrisp knows the data is already in your hand, in R6. So it looks at 1 plus and fuses the opcode and the constant into a single ARM instruction.
It just emits adds R6 #1.
Precisely. It doesn't generate overhead. It generates the exact same tight instruction a human assembly programmer would write.
So it skips all the middle management. And the document mentions an even more extreme version, the RA variant.
Oh, the register allocator variant,
But
yes.
it's amazing. If the standard version has one document glued to its hand, the RA variant essentially grows multiple arms.
It really does. It actively tracks the top 5 stack elements.
Right, mapping them dynamically into CPU registers R0 through R3 plus R6. The source cites this Bitex example.
Yeah, the math operation.
It compiles down to 14 ARM instructions with absolutely zero stack memory traffic. It just uses an inline cache buffer.
What's fascinating here is how that obsession with avoiding overhead extends to how the language builds its own dictionary.
Oh, the word pair. Let's talk about that.
Yes, because Forth is interactive. When you invent a new command, a word, in Forth, it has to be saved into the chip's permanent memory.
So you can use it later.
Right. And Mecrisp handles this using a complex assembly macro called wordburn, which is German for word pair.
I just love that name. What does the word pair actually do structurally?
It builds each new Forth word as a linked list node directly in the flash memory of the chip.
And it packs all this metadata into the status flags of that node, right?
Exactly. It uses specific bits to encode the word's visibility, whether it should execute immediately during compilation, and its emerity.
Arity meaning exactly how many arguments the word consumes and produces.
Right. So the compiler always knows the exact shape of the data flowing in and out.
It's such an elegant system. And clearly, the embedded hardware community recognizes the brilliance here. The source summarizes that it supports over 90 different chip variants.
Everything from legacy STM32 chips to the Raspberry Pi RP2040.
And it has all these turnkey features. But this brings up a logical bridging question for me.
Okay, let's hear it.
If it's this incredibly optimized and powerful, running on 90 different chips, what's the catch? Why isn't every embedded developer using this in 2026?
Well, because that extreme purity comes with serious quality of life costs.
The UX nightmare.
It is an absolute UX nightmare. You might have a Ferrari of a compiler, but the dashboard is broken. Let's start with the stair-stepping bug in the REPL.
Oh man, the stair-stepping. For you listening, this is incredibly frustrating.
It really is. When you hit the Enter key on a terminal, historically, it expects a carriage return to bring the cursor to the left and a line feed to move it down.
Like an old typewriter.
Exactly. But Mecrisp, to save literally every single byte, emits a space instead of a carriage return and only sends line feeds.
So when you cold boot it and hit Enter, your text doesn't go left.
Nope. It just drops down one line and stays indented. Then you hit Enter again, it drops down and indents further.
Like it's walking down a staircase off the side of your monitor.
Yes. So you have to rely on these ugly terminal workarounds, passing flags like --emap, lfchar into programs like pico.com just to read your screen.
So what does this all mean for the developer? You have a fast compiler, but it's physically annoying to use.
Right. But that's just a surface level issue. The biggest functional weakness is peripheral blindness.
This part blew my mind.
The kernel is basically a genius brain floating in a jar. It has no detailed peripheral knowledge. It only knows how to talk to exactly one hardware component, the internal UART.
Which is the serial port that lets you type at it. But that's it. It doesn't know about GPIO pins, SPI buses, USB, nothing.
Nothing. Everything else has to be manually hand-coded using raw register addresses.
The source gives this brutal example. If you want to configure a clock, you can't just type enable clock. You have to manually type $400 to 1000 constant RCC BSE.
Just to get the memory address.
I shudder just thinking about having to look that up in a 500-page PDF datasheet.
Oh, it's brutal. And if you make a typo in that hex address, the chip just hard faults.
And on top of that, it's hostile to modification, isn't it?
Very. This brings us to the sad reality of the project's status. It's essentially at its end of life. Matthias Koch's last release was November 2022.
Version 2.6.5.
Right. And because the core is a monolithic 15,000-plus line block of assembly, it's beautiful, but it's completely hostile to anyone else trying to modify it.
Because if you touch one thing, you might break a hard-coded register offset somewhere else.
Exactly. So toolchain rot is setting in, and silicon bugs remain unpatched.
Like the M4 LDMIA corruption bug mentioned in the notes.
Right. That's a physical defect in early Cortex-M chips, where a hardware interrupt can permanently corrupt the CPU state during a multi-register load.
And because Mecrisp is so minimal, there's no built-in exception handling to catch it.
It just crashes. Now, in a proprietary software world, an abandoned 15,000-line assembly project with a broken interface would just die.
People would just move on to the next shiny tool.
Exactly. But this is open source. It's GPL v3. So how does the embedded community in 2026 fix a core they can't easily rewrite?
They build a bridge around it. And here's where it gets really interesting.
The community basically bypassed the serial port entirely.
Right. They introduced a project called SWD-COM. Instead of relying on that old on-chip UART that causes the stair-stepping bug, they moved the REPL to the SWD interface.
The serial wire debug interface.
Explain the two-wire magic of this, because this is why it matters so much.
Okay, so historically you needed two separate cables.
Okay.
A debugger to flash the chip, and a USB to serial adapter to type commands.
Right.
SWD-COM means one cable handles both flash uploading and the interactive REPL over just two wires, SWDIO and SWCLK.
And crucially, the host PC side handles the CRLF formatting now.
Yes. It instantly kills the dreaded stair-stepping bug without touching the assembly core.
That is such a clever workaround. But I need you to unpack another detail from the source. It mentions a 512-byte synchronized cache. What does that do for the debugging process?
It enables completely non-invasive debugging.
Okay, non-invasive meaning the CPU doesn't get interrupted.
Exactly. With a normal UART, transmitting texts steals CPU cycles. It blocks the processor.
So the chip has to pause its actual work to send a text message to your screen.
Right. But with the 512-byte cache, the MCU just drops the data into a memory buffer and goes right back to work in microseconds.
Oh, wow.
And then the host PC asynchronously pulls that buffer over the debug wires. It allows for speeds over 1 megabit per second without blocking the CPU.
That is a massive leap forward. The CPU basically just leaves a note on the table and walks away, and the PC reads it without bothering anyone.
That's exactly how it works.
But we still have the $421,000 nightmare, right? The peripheral blindness.
Right. We need to know how to turn the clock on without reading a 500-page manual.
And that brings in the final piece of the puzzle, FURS.
FURS solves that exact problem.
It uses CMS ISISVD files, right?
Yes. Chip manufacturers provide these massive XML files called SVBs, which map out every single peripheral and memory address on the chip.
So FURS parses those XML files.
And it generates structured, type-safe, registered definitions automatically.
So you don't have to bit-bang raw hex anymore. You get clean, human-readable commands.
Exactly. This synergy here is just beautiful.
Let's synthesize all three of those elements for the listener.
Okay, so Mecrisp gives you the blazing fast on-chip compiler. FURS gives you the modern peripheral abstractions. And SWD-COM gives you the modern, non-blocking hardware connection.
It's like strapping a modern navigation system and a new transmission onto a classic Ferrari engine.
Exactly.
So bringing this all back to you, the listener, whether you're an embedded engineer or just someone curious about tech, why should you care about any of this?
I think it represents a true masterclass in software longevity.
Right. It shows how community-driven FLOSS tools, free Libro, and open-source software can take an aging, idiosyncratic masterpiece and actually challenge proprietary vendor IDEs on their own turf.
Proprietary IDEs are often bloated, gigabytes in size, and they abstract you entirely from the hardware.
But this setup gives you a Python Forth hybrid IDE feel, right?
Yeah, it brings interactive register-level debugging to bare metal, but without the historical pain points of embedded Forth. You get the best of both worlds.
It really is an amazing story of community engineering. But before we wrap up today, I want to leave you with a final thought to mull over.
Oh, this is a good one.
Think back to the Wurtbrand macro. We talked about the word pair.
The one that maps every new word directly into flash memory.
Exactly. Since flash memory physically degrades with every single write cycle, and interactive development requires constant writing and tweaking of new words, the very philosophy of this compiler requires physically degrading the chip just to explore and compile new ideas.
You're slowly destroying the hardware just by coding on it.
Right. So at what point does the cost of living on the metal and burning through that hardware outpace the benefit of never needing a PC-based compiler?
It really makes you think about the physical cost of software.
It absolutely does. Something to explore on your own. Thank you so much for joining us on this deep dive.
Thanks for listening, everyone.
We'll catch you next time.